properties of rational exponents. So, the properties dealing with, like, rational exponents and stuff are the same as our normal exponent rules. So, like, you know, a to the m times a to the n is equal to a to the m plus n. All those are the same, so I'm not going to, like, rewrite those. Just remember those from when we did exponents. But we do also have properties of radicals. And I'm sure you've seen this, like, kind of before, but the nth root of a times b is equal to the nth root of a times the nth root of b. And this is the product property of radicals. And then we also have the nth root of a divided by b is equal to the nth root of a over the nth root of b, assuming that b is not equal to 0. And this is the quotient property of radicals. So we're going to move into examples of this stuff, and yeah. So the first one say to simplify the expression. So something like number 4, 6 raised to the 2/3, all raised to the 1/2. So when we have a power raised to a power, what do? Yep, we're going to multiply the powers. So that will be 6 to the 2/3 times 1/2, which gives us 6 to the 1/3. And you can either leave it like that, or if you want to write it as the cube root of 6, either of those answers would be fine. And since you're, like, multiplying, you don't have to, like, write this step out. You can just go straight to here and, like, just multiply that, you know, in your head. I'm just writing it out so you can see it. 7 cubed over 4 cubed raised to the negative 1/3. So what does the negative 1/3 do for us? Or what do we need to do with it? Yeah, flip it. So it's on the whole thing, so I need to flip the fraction. So this will become 4 cubed over 7 cubed, all raised to the 1/3 now. And then what happens when I have, like, a fraction and it's all being raised to an exponent? What do I do with that? Multiply. So we're going to end up multiplying the top piece, like the top exponent by that, and then the bottom exponent by that. So this would be 4 to the 3 times 1/3, and again, you wouldn't have to write this step, but, and then 7 cubed times 1/3, which ends up just giving me 4 over 7, because the 3's cancel. So it's basically same stuff that we had done with, you know, normal exponents. It's just now we have rational exponents involved with them. Let's do one that's a little harder. Number 12. 64 to the 5/9 times 64 to the 2/9 over 4 to the 3/4. Any ideas what I should do first?
Add the 64 exponent.
add the exponents on top. So that will give me 64 to the 7/9. Any idea what I can do on the bottom to try to get the same base?
Can't you do 4 outside the square root or 4 cubed?
Well, I'm trying to get the same base as 64. So what power is this being raised to? Like, obviously, like, the one thing is a root. So what is the power that's on there?
Cubed.
It's cubed. What is 4 cubed?
64. Yeah.
64. So that would give me 64 raised to the 1/4. And now I need to look at reducing this. So how would I do that?
Good. 64 7/9 over, or forget 1 over 64 7/9. Multiply. Both sides.
Not exactly.
Thanks, Joshua.
So when I have something like 5 cubed over, well, let me do this. 5 to the 4th over 5 squared. What did we do with that? Maybe let me take out numbers so that I do it with x's. Subtract the exponents, right? So that's what I'm going to do here. So this is going to become 64 to the 7/9 minus 1/4. So then I need a common denominator up there to be able to subtract them. What would my common denominator be?
36.
36. So 64 and then 36. So that would be multiplying the first one by 4. So 28 minus the second one times 9. So minus 9. So this would end up giving me 64 raised to the, what was that, 19 over 36. And that would be where we would leave that. Now, it could potentially, you could do something with it and make it go farther, but that's where I would tell you to leave it. And that's what I'm going to tell you about this section in the book is sometimes they may go farther with it. Like their final answer, just in case you're so inclined to want to know, is 8 times 2 to the 1/6. Because of how they ended up breaking things down and all of that. I would just leave it of what I have in blue. But just know that just because your answer doesn't match the back of the book when you're checking doesn't necessarily mean that it's wrong. If you need me to look at one because of that, just let me know. Simplify the expression. So these are going to be with radicals now. So number 16, the cube root of 16 times the cube root of 4. So since these have the same root on them, I can multiply what's inside of them and have them all under the 1 cube root. So this is going to be the cube root of 16 times 4 is 64. And then now, sometimes once you get to here, you can actually take the cube root, which in this case I can, right? What would the cube root of 64 be? 4. So this one would just be 4. And just something to remember about this is if you had something that say you didn't know what it was, to try to break it down and simplify it, because that's the goal, is to simplify it as much as possible, is we can take 64 and break it into like 8 and 8, and then like 2 and 4, 2 and 4. And since I have like 3 4s, I can take a 4 out. because it's a cube root, right? So if it was like something raised to the 4th power, if I have 4 of them, I can take it out. So just remember like that little piece of information there. 18. The, in parentheses, cube root of 3 times the 4th root of 3 raised to the 12th. So can I multiply this stuff under the radicals on this one?
No.
Why not?
Wait, oh no, because you have two different
Right, yes.
groups.
Yeah, that's just what I'm just trying to get you to it's a little bit of a trick question. I'm just trying to get you to tell me why. So they have different roots on them. So I need to, though, raise everything to the 12th power. So probably the best way to go about this is to write these in terms of rational exponents to deal with it. I just think it makes it easier. So this would be 3 to the 1/3 times 3 to the 1/4, all raised to the 12th. And so if you want, there's two different ways you can go about doing this at this point. You can either go ahead and do normal like PEMDAS, right, and combine the stuff that's in parentheses first by adding the exponents together, but then that means you need to get a common denominator to be able to add them, which obviously these numbers aren't hard, but then take that and raise it all to the 12th power. The other option is we can just multiply each thing in here by 12 and get it that way, which is the easier way to do it. So this is going to become 3 to the 1/3 times 12, which would be what? What's 1/3 times 12? 4. So 3 to the 4th times, what's 1/4 times 12? So then 3 cubed. And this would end up giving you what? 3 to the 7th. And I'm okay, again, with you leaving it there. The book will basically plug that in the calculator and get an answer. And if you were just so inclined to want to know what that's equal to, it is 2,187. But I'm content with you leaving it as whatever the number is raised to the power. I mean, if it's like 3 cubed, 3 to the 4th, I mean, something like that you should know, yeah, multiply it out. But I don't expect you to know 3 to the 7th without having to, like, sit there and write them all out. I'm mainly looking that you can deal with the exponent situation. 22. The 4th root of 8 times the 4th root of 16 divided by the 8th root of 2 times the 8th root of 3. So any idea where I should start with this one?
You can combine 16 times 8,
Yep. So it'll be the 4th root of 8 times 16 and then the 8th root of 6. Now, at this point, obviously our goal is to simplify. So I would see if there's anything that I can take out of the radical on top, like anything that I would have a group, like groups of 4 of that I could take out to try to simplify it down as much as possible. So, let's see, I'll do it down here. So 8 and 16, I can break up into 8 is 2 and 4, 4 is 2 and 2, 16 is 4 and 4, 2 and 2, 2 and 2. So I've got 1, 2, 3, 4, 5, 6, 7 2s, so I can take out 4 of them. and be left with 2 times 2 times 2 inside. So this will become on top 2 the 4th root of 8 over the 8th root of 6. But I have a problem because I can't have a radical on the bottom. So I need to do something with this. So at this point, might be good to convert these into rational exponents to deal with it. So how would I do that? How would I rewrite this stuff? Well, I'm trying to get rid of the square roots. I want to rewrite them as exponents. How do I rewrite the roots as exponents?
Times 8 to the power of 1/4 equals 6 to the power of 1/8.
Now what? Can I do it? Well,
You can
Yes.
subtract.
but can I do anything because they're different bases? No. So I'm going to actually let you leave it there because there's nothing else. Either here or here, because the way to get rid of that is just, I don't know why it's crooked. Anyways, the way to get rid of it is complicated, but clearly as the boxes as well. But yeah, you can just leave it like that. I was thinking they were the same base and it was going to cancel out and it didn't. So either way of that, you can leave it. I don't care. Some of the problems in this section, forgot how much I don't like them. All right, let's do one of the ones where we're like breaking it down and actually being able to take stuff out and it'd be easier. So 26, the cube root of 108 times the cube root of 4. So ultimately I'm trying to break these down. Are either of these a perfect cube? No. So I can multiply the stuff that's inside of there. I don't even need to actually multiply it out though. Like I can just write it as the cube root of 108 times 4 because when I do my little factor tree, I'm just going to be breaking it down. So there's no point in me putting it together to break it back down. So I would just start with 108 and 4 as the factors that I'm breaking down. 108, 9 and 12. 4 is 2 and 2, so I'm done with that one. 12, 3 and 4. 4 is 2 and 2. 9 is 3 and 3. So anything that I have groups of 3 of, I can take out. So I've got 3 3s, so I can take a 3 out. And I've got 3 2s, so I can take out a set of 2s as well. So this would be 3 times 2 times the cube root of 2, which ends up being 6 cube root of 2. Like that.
Wait, how'd you get the 2?
Huh?
How'd you get the 2?
Under here?
Yes.
So there was one left when I was
Oh.
done factoring it out and breaking it down. So I had to have groups of 3 and there was one left over.
Oh, okay. That makes a lot of sense.
All right, simplifying the expression, which obviously a lot of these say that, but they're like different like topics within this. 32, 2 times the 6th root of 3 plus 7 times the 6th root of 3. So when adding and subtracting radicals, we need to make sure that just like when we have like variables, we have to have like terms, okay? So we have to have like radicals. So I have the 6th root of 3 and the 6th root of 3, so that means I can actually combine these. So when I add those together, I will end up with 9 times the 6th root of 3. Now, something like 36, though, 6 times the cube root of 5 plus 4 times the cube root of 625. So, can I add these together? Or does it look like I can add them together? No. But could I maybe try to break the 625 down and see if I can pull something out and, like, maybe it'll work? Yes. So, and sometimes you might try to break it down and it won't, and the answer just is the problem, but let's see what happens if I do that. So, 625, let's see, I could take out a 5, and what is that going to leave me with? 1, is that 175? I don't think so. 1, I think it's 125.
Yeah.
Okay. And then still got a 5, so let's take out another 5. And if I do that, I'm left with 25. 25 I can break into 5 and 5. So I have 4 5s. So I can take out a 5 from everything, and I'm going to be left with 1 inside. So this would be the 6 times the cube root of 5 plus, take the 5 out, so 5 times 4 is 20 times the cube root of 5. Now I can add them together, and I would get 26 times the cube root of 5. So sometimes you have to break it down first to be able to do that. And if nothing else, I mean, at least breaking it down is, sufficient to show the work that you did for that. So some of what we've done, they also do with variables. I'm just going to show you like one of each of the ones with the variables because they work the same way. I'm trying to find one that I want to do. 48. The cube root of x to the 15th over y to the 6th. So I can, because it's a radical of a fraction, I can split it top and bottom. So I'll have the cube root of x to the 15th over the cube root of y to the 6th. So I need to see about pulling things out in groups of 3s. Now these ones kind of work out nicely, but how many sets of 3 would be in x to the 15th? 5, and it comes out even, so it's, works out nicely. So x to the 5th would be the top. And then how many sets of 3 can come out on the bottom? 2. So that would just be y squared. So nice and easy. Oh, it's 10:46. Okay, yeah. Well, we'll finish up like 1 or 2 more examples tomorrow, and then I'll give you problems to do, and then you'll just have the rest of the time to work on them. So it's not a hard section, I don't feel like, but it's just kind of long, and obviously a shorter class, so.